Okay, hello everybody. We are going to be doing the spring 2016 Orgo 2 exam. And to get started, we have our nomenclature. All right, so for this first question that we have two double bonds in the structure, and those are our only functional groups. So when we have multiple double bonds in the structure, we want to try and get as many of those incorporated into the parent chain as possible. And so luckily with this one, we can see that there's a easy way to get both of those added on. Sometimes it's a little bit more tricky when you have more double bonds, like 3 and up, but luckily we only have 2 here, so we can get both of those incorporated into our main chain. So I started numbering right to left, and I'm going to go ahead as well and number the reverse direction. And when we do this, we want to get the longest chain possible, and we want to get the most amount of substituents as possible as well. Specifically with our double bonds, like I mentioned before, we want to try and get all of those incorporated into the main chain as possible. So that's why I went the direction that I did. And so from here, we need to compare the different numberings to see which one is going to give us the lowest number substituents. So if we're looking at the orange, we have a methyl group on carbon 2. We have a purple group on carbon 4. We have another methyl group on carbon 6 and another methyl group on carbon 7. If we're looking at the blue numbering, we can get a methyl group on carbon 2, a methyl on carbon 3. We have our propyl on carbon 5, and another methyl on carbon 7. So since the blue numbering overall gives us lower numbers, we're going to go with that as our parent chain direction. I'm just going to go ahead and erase the orange numbering so we don't confuse ourselves. All right, so I like to break up the nomenclature into 3 different parts. We have our parent chain, we're going to have our substituents, and then we are going to have any stereochemistry if it's applicable. And that's just going to be RS, EZ, or cis and trans. All right, so let's not get too ahead of ourselves though. So we have an 8-carbon chain, so that's going to be octane. And then because we have 2 double bonds in there, we're going to have to switch that to our alkene nomenclature. So you want to start numbering your double bonds at the beginning. So we're going to have a 2 and a 4 for our alkene nomenclature. So we're going to switch this octane to be 2, 4 octadiene. And don't forget the di prefix. That indicates that we have 2 double bonds in there. Another way that you could do this, you could also throw the numbers in the middle of the naming there. So you could have octa 2, 4 diene, and both of those would be accepted. Okay. So going on to our substituents, we already determined the numbers. Now we just have to figure out what the substituents are. So again, we have a 2-methyl, we have a 3-methyl, and we have a 7-methyl. And so when we have multiple of the same substituents, we're going to throw them onto the same, we're going to kind of combine them. So kind of like we did with the diene, the 2,4-diene, we're going to put these methyls as 2, 3, 7, and since we have 3 of them, we're going to have trimethyl. And then for our last substituent, we have a 5-propyl. Propyl is going to be the 3-carbon chain. So we got that 3-carbon chain there. That's going to be our 3 purple. That looks like a 5. And that is going to be all of our substituents. So just double check. We got all of them. We're good to go. Last thing to worry about is going to be our stereochemistry. So when we have double bonds, we can go through either the EZ or the cis and trans nomenclature. The only time you can do cis and trans, however, is going to be when you have 2 hydrogens on the double bond. And that's because cis and trans is actually referring to the hydrogens, not actually the substituents or the R groups that are on that double bond. So just starting with our first double bond here, we're going to take a look at the groups that it has. So on the right over here, we can see that we have 2 methyl groups coming off of the same side. And since these groups are the same, we can't actually determine a difference in the priority between them. So we actually will not have E and Z for this first double bond here. If we look at the second double bond, however, at carbon 4, we do see that we have differences between the R groups that we have. So just starting on the right, we have this carbon chain branching off for the rest of our structure. And then the other atom that's attached would be a hydrogen there. So if it helps you to write out the hydrogens, I highly encourage that. And then when we compare these two, we're going to look at the priority of the atom. And so the higher priority goes to higher atoms on the periodic table. So hydrogen is obviously first on the periodic table, so it's pretty much always going to be our lowest priority. And then going up to the right, we have a carbon, so that's going to be our higher priority on this side. So when we go to the left over here, we've got some carbon chains coming off, and it's not immediately apparent which one is going to be the main chain. So if we look at carbon 6, this carbon is going to be connected to this carbon going up and to the left, and then it's also connected to 2 hydrogens. So this one's going to be CHH. And then if we go to our first carbon on the propyl chain, we notice that this also is it's got the same connectivity. It's connected to a carbon and it's got 2 hydrogens. So that one's also CHH. So since they're the same, we're going to have to go on to the next carbon. So we're comparing carbon 7 and carbon 2 of the propyl chain now. So with carbon 7, we can see it's connected to 2 carbon groups, and it's got a hydrogen on itself. So we're going to say that's going to be CCH. If we look at carbon 2 of the propyl group, we see that it's connected to 1 carbon and 2 hydrogens. So CHH. So when we compare these two, we're going to go with the top chain as our higher priority because it's connected to more carbons. All right, and so since the high priority groups are on the same side, that nomenclature is going to be Z. Or sorry, that stereochemistry is going to be Z. And so one way to remember the difference between E and Z is that Z, they're on the same side. So it sounds kind of like same. Okay, so now that we have our stereochemistry, we can go ahead and throw it all together. So our stereochemistry goes first. We have Z. We have our substituents. Make sure to put them in alphabetical order. So we're going to be comparing M versus P. M comes before P. So we're going to go with that as our first substituent. So 2,3,7 trimethyl. Then we've got our 3 propyl. And finally, we're just going to throw our parent name at the end. So again, you could go with either of the numbering, either before or in the middle of the parent name. Either one is fine. So octa-2,4-diene. So that is going to be our name for that one. Just a note about the E and Z. When you only have one double bond that has an E or Z stereochemistry, you don't have to worry about putting the number. If you have multiple, however, you would have to worry about putting the number. So for example, since this double bond starts at carbon 4 and we determined that it was Z, this would be 4Z. So since we only have one, we don't necessarily have to put the number. But if you would like, if it helps you to kind of remember when you do have multiple double bonds, you can put the number and either one would be fine. Okay, so that's going to be our first nomenclature, and now we're going to go on to the second. So this is going to be our epoxide. And so epoxides can be named in multiple ways. You can do the industry naming system. You can do the naming where you kind of go along the parent chain or the bottom chain and name it as a epoxy substituent, or you can do the oxyring nomenclature. And I don't really recommend the industry nomenclature just because you'd have to memorize the name of an industry molecule, and we already have to memorize so much that I just don't think that's a very good use of our time. But I will go over both the epoxy substituent nomenclature and the oxyring nomenclature as well. Okay, so similar to other nomenclature, when we go along the epoxy substituent route, we want to get the lowest number for our substituents and the longest chain possible. So our epoxy is going to be a substituent, and this OCH3 group is also going to be a substituent. Ethers are going to be substituents. So we can either start numbering from the left to right, or we can start numbering from the right to the left. So when we go left to right, our substituents are going to be on 3, 4 for the epoxide, and then 7 for that, that ether group. If we go the opposite way, we get our ether on carbon 1, and then our epoxide on carbon 4 and 5. And so the orange numbering is going to give us the lower numbering, so we're going to go with that. All right. So our parent chain, 7 carbons, we're going to have a heptane. All right, and then for our substituents, again, we've got this ether. And so remember, ethers are going to be named as alkoxy groups. So in this case, we have a methyl on that ether oxygen. So this is going to be methoxy, and that's on carbon 1. So then for our epoxide, we're just going to name it as epoxy. And so we're going to put both of those carbons that it's attached to, because it's important to note specifically which carbons the epoxide is at. And then we're just going to put epoxy. So this is going to be 4,5 epoxy. And then we don't have any other substituent on that chain. So we just got our subs here. And the only other thing that we're going to have to worry about is the stereochemistry. So when it comes to stereochemistry for epoxides, you have a couple of options. You can either do cis and trans, or you can do R and S. Now, the only time you can do cis and trans is when you have 2 hydrogens attached to that epoxide structure. And again, that's kind of like the alkene. The cis and trans refers to the hydrogens themselves. So you need 2 hydrogens to be able to make that cis-trans comparison. In this case, we do, which is good because cis and trans is a lot easier than trying to determine R and S. But you could also go the R and S route if you wanted to. So in this case, I'm just going to use cis and trans because it's a little bit simpler. And so in this case, the hydrogens are on the same side, so we've got cis stereochemistry. So we've got our parent, we've got our subs, and we've got our stereo. So we're just going to throw that all together. So we've got cis. Again, alphabetical order for the substituents. So we're comparing M versus E. E is going to come first. Epoxy. and then 1-methoxy. And then our parent name is just heptane. All right, and that is the nomenclature for the epoxy substituent naming. So I will also go ahead and go over the oxyrain nomenclature, just because that is another one of the valid options. Again, I don't really recommend industry naming. It's just a little bit more complicated, but oxyrain is also a valid option. So for this one, the parent is going to be oxyrain. And so oxyrain is that that basic epoxide, and then we're going to have to name the subs as the groups that are coming off of it. So when we have ring structures and we have substituents coming off of them, we always have to remember we need to start numbering from where they are connected to that parent ring. So we're going to start numbering in this way. We're going to go ahead and do that on the other side. So over here on the left, we've just got an ethyl group, 2-carbon chain. That's going to be ethyl. And then on the right, we have a little bit more complicated substituent. So we have a propyl base chain with that 3 carbons. And then this methoxy, again, is going to be a substituent. And so since this substituent has its own substituent, that's going to be a complex substituent. So we're just going to put that methoxy in front of the propyl. And we're going to have to denote what carbon that is at. So again, make sure that we number correctly. We're numbering off of the chain itself. And so that puts the methoxy substituent at carbon 3. And so with a complex substituent, we throw it in parentheses, and then we'll have the number of that whole substituent come out in front. So when we're determining the numbering of these substituents for oxyrain, oxygen always comes first. And then we are going to do alphabetical order. So ethyl comes before methoxy. So in this case, the ethyl group is going to be carbon 2, and the complex substituent that we have is going to be at carbon 3. So this is going to be 2-ethyl and 3-methoxy propyl. Okay. So we've got our subs, and then the last thing we have to worry about is going to be our stereochemistry. And so again, you can either do cis and trans or RNS. So similar to what we did before, we can just give it that cis nomenclature. But if you would like to as well, we can go over the RNS. So if we are looking at the RNS, this is going to follow the same rules as the E and Z in terms of priority. So we're going to give the higher group on the periodic table the highest priority. So in this case, oxygen is going to win, comparing on the left carbon, sorry. Oxygen is going to be the highest priority. Hydrogen is always going to be our least priority. And then we just have these 2 carbon groups that we have to look at. So if we look at the carbon going down on the ethyl chain, we see that it's connected to a carbon over here, and it's got 2 hydrogens. So this is going to be CHH. And then going to the right off of this, the carbon in the epoxide ring, we see that it's connected to this carbon is connected to the oxygen up top, and then a carbon going down to the bottom, and that hydrogen. So this oxygen is going to make this the winner. So we're going to have our priority be 2, and then the ethyl chain is going to be 3. So we can just rewrite that up here. We had 1, 2, and 3. And so going around the going around the numbers, we've got our R. Yeah, our R. And hydrogen is on the dash, so we're good to go. We don't need to do any switching. And so we've got R. And again, we've got two RNSs that we need to consider, two carbons that have R and S that we need to consider. So we're going to have to put the number for this one. So this is going to be 2R. So we're just going to do the same thing for the carbon 3. So again, the oxygen is going to be number 1 priority, hydrogen is going to be 4 priority. And so kind of with the same concept as the last carbon, going down the chain, we just have a CH2 group, but going left across the epoxide bond, that carbon is going to be connected to an oxygen again. So that would give us our priority. So we're going to go with, again, into the epoxide chain as 2, and then off the substituent as 3. So just rewrite that up here so we can kind of get a better idea. So when we go around the numbers this time, this is going to give us an S stereochemistry. So again, just don't forget the number on this one. So this is going to be 3S. So with this one, you could do the cis nomenclature, cis trans nomenclature, and I'd probably go with that because it's a little bit simpler, but you can always do the R and S as well if you would like. So when we throw this one together, we've got our substituents. Oh, sorry, we got our stereochemistry first. 2R, 3S, and then we've got our substituents. So again, we're going to be comparing methyl versus ethyl. Ethyl is going to come first. So we've got 2-ethyl. We've got 3 dash comma 3 methoxypropyl. And then we've got our parent name, which is going to be oxyrane. So that would be the nomenclature if you wanted to do the oxyrane nomenclature. And again, you could either do the RNS or you could do the cis and trans. Either one would be correct. Okay, so now we're going to go on to our final nomenclature. And so one thing to consider when we're doing nomenclature is that right now, alcohol is our highest priority functional group. So that's going to take priority over alkanes, alkenes, alkynes, and even ethers and epoxides. So when we look at this structure, we see that we have an ether over on the left and we have this alcohol over here on the right. So we're going to want to put the alcohol on the parent chain because that's going to give us our parent functional group. And we also want to give that parent functional group the lowest number possible. So even though if we numbered left to right, we would get lower number substituents. We'd get 1 and 4 versus if we went right to left, we would get 2 and 5. We're still going to go with the orange because we're actually not considering the alcohol as a substituent. It is the parent chain. So don't get confused about that when you're looking at the parent chain. Okay. All right, so throwing our numbers back up there. So our parent is going to be a 5-carbon chain. So that's going to be pentane. And then we've got that alcohol, so we're going to switch that pentane to be a pentanol. So the alcohol is at carbon 2, so it's going to be 2-pentanol. Or you could also do pent and 2-ol. Either one of those would be fine. All right, so now we're going to be going on to our subs. And so, again, alcohol is not a sub, it's a parent. So the only substituent that we have is going to be this ether group over here. And so Again, ethers are named as alkoxy groups, so we're just going to throw that alkane name, so cyclohexane, and that's just going to be cyclohexoxy. So it's a little bit cyclohexoxy. It's a little bit wacky, but just remember that we're going for the alkoxy nomenclature. So just name it like you would a normal alkane, cyclohexane, and then switch it to be the oxy ending. And that substituent is at carbon 5 on the parent chain. So that's our only substituent, so we're good to go on that. And so the last thing that we're going to have to worry about is our stereochemistry. All right. So we've only got one stereochemistry that we need to worry about here. We've got these wedges and dashes that indicate the stereochemistry that we need to look at. And so for this one, we're going to have to do R and S. All right, so we just had some practice with that, so we should be good to go. So again, the highest number on the periodic table is going to give the highest priority. So oxygen is going to be our number 1, hydrogen is going to be our number 4. And then we've got these 2 carbon chains to look at. So going to the left, we can see obviously that this chain is bigger. It's going to be connected to more carbons versus this group on the right, which is just a CH3. So going to the left is going to be our number 2, and the CH3 is going to be our number 3. And so again, just put those off to the side, make it a little bit easier to see. So we're going to be going 1, 2, 3, and that's going to be R. And so our lowest priority functional group is on the dash, so we're good to go. We don't need to switch that up. It's going to stay R. And that's all of our stereochemistry. So again, similar to the first example, if you only have one R or S or E or Z, you don't have to worry about putting that number in there. But if it makes it easier, just so you can remember for the future, you can put that number in there as well. So that would be 2R. Okay, so then we just throw our name together, 2R. Our subs are 5-cyclohexoxy. And then our parent name is pentanol, or 2-pentanol. Either one is fine. Okay, so that's our nomenclature done. And now we're going to move on to the fact section. All right, so for this first one, we're looking at resonance contributors for stability. And so in this case, we see that we've got some carbocations going on. So just remember, for carbocation stability, tertiary, secondary, and then primary. Tertiary is going to be the most stable, and primary is going to be the least stable. All right. So in this first structure, the positive charge is on the oxygen, so we're not actually going to be looking at carbocation stability. For the second one, we see that the carbocation is on a tertiary structure. It's got 1, 2, 3 R groups coming off. In the structure on the right, this carbocation is connected to one other carbon group, so that's going to be primary. So between these two, we can see that our primary carbocation is going to give us very low stability. We do not want that. And now, although we have this tertiary carbocation, we still have to consider the structure on the left to see which one is going to be more stable. So on this structure, we see that we don't have any carbocations, but this oxygen has a positive charge. Now, when we're looking at stability, the biggest factor is going to be the octet rule. And so that's just saying that does each carbon have, or sorry, not carbon, each atom have 8 electrons. And so when we have the octet rule satisfied for all the atoms, that is going to be the most stable structure. So this carbocation over here, although it is a tertiary carbocation, it only has 6 electrons, so its octet rule is not satisfied. So this is actually going to be less stable than this oxygen over here on the left. So we're going to put this structure on the left as 3 and the structure in the middle as 2. And so another factor that we sometimes consider for these is the charge of the atom. But don't get confused. Even though oxygen is electronegative and is less stable with the positive charge, this octet rule is going to overrule that charge factor. The octet rule is going to be the big one that you want to look for. So that's why we went with the left as number 3 instead of the middle. Okay, so we've got some more stability that we got to look at, alkenes. So for alkene stability, alkenes are more stable with more subs. So we're just going to look at all of these alkenes and see if they are mono, di, tri, or tetrasub. And that just means the R groups that they have coming off of them. So looking at this first structure on the left, we've got our alkene over here on the right, and we're just going to look at the groups that come off of it. So this is going to be a tri-substituted alkene. Going on to the second, we've got 2 R groups coming off of that double bond, so that's going to be a disub alkene. And then over here on the right, this is going to be a tetrasub alkene. And so, again, the alkenes are going to be more stable with more subs. So the most stable is going to be our tetrasub structure over here. The trisub will be our next most stable, and then the disub in this case is going to be the least stable. All right, so moving on to the third question. So we've got reactivity in NaOCH3 and CH3OH, and so we're going to see if these compounds react with that reagent. So when we look at NaOCH3, keep in mind that this is going to be an ionic pair. So that sodium is positively charged, that oxygen is negatively charged. And so when oxygen has a full negative charge like that, it's going to act as a strong base. All right, so when we look at our structures, we have an ether over here on the far left. And so ethers are only really going to be reactive to strong acids. And that's because the oxygen in this structure is pretty stable. The only way that we can get it to react is if we protonate it and activate it. But in this case, since we have a base, we're not going to be able to do that. So in this case, this will not react with our reagent. Again, that's just because ethers are really only reactive to strong acids, and we have a strong base, so it will not work. Going on to our second structure, we have a alkyl halide. And so if you remember from organic 1, we have a tertiary alkyl halide. And so this is actually going to be reactive towards our reagent. And so this is kind of similar to like an E2 or like an SN2. Well, technically not, because SN2 is primary, but SN1, E1 reaction. So if you remember from organic 1, what would happen is the nucleophile would come in and attack the partially positive carbon, and that bromine would get kicked out, and we'd form an ether that way. So this one is going to be reactive towards that reagent. All right, so over here in our third structure, we've got an MgBr Grignard reagent. So this one's a little bit unique. So again, one thing to keep in mind when you have these first and second row metals is that often they are forming ionic bonds with these structures. And so the the alkane part of this structure is actually going to be a carbocation. And so that's important because although we have OCH3 minus in this system, we also have CH3OH. And so when we have this methanol, what will happen is this negative carbanion in this Grignard reagent will be able to deprotonate that methanol. So this one is not reacting with the OCH3 itself, but it is reacting with that methanol solvent. So this one will react. Okay, so going on to our last structure, we've got an epoxide. And so one thing to note about epoxides, although they look similar to ethers, they're both oxygens connected to an R group on either side. Epoxides are a little bit unique in that the ring strain that they have makes them a lot more reactive. All right. And so in this structure especially, we've got this carbon over here on the left that's only got one other methyl group coming off of it. And so with this partially positive carbon, our reagent, the CH3O minus, can come in and attack that partially positive carbon, and that will kick up our epoxide to form a new structure. But overall, this one is reactive enough to react with our reagent. So we're going to put a yes in that box there. All right, so that's reactivity for NaOCH3 with our structures. And now we're going to go on to a Deals-Alder question. All right, so in this question, we're being asked basically to find the precursors to this dienophile product, Deals-Alder product. And so one thing to consider is just to remember the basic structure of our diene and our dienophile. It's got to have at least one. It's got to have at least one withdrawing group, and it's got to have at least one double bond. So when we look at this structure, we can see over here on the right that we've got some carbonyl compounds or carbonyl groups. And so those are going to be electron withdrawing. So we're going to look at this right half of this structure and see that that's going to be our dienophile precursor. And when I do these questions, I like to look at the dienophile first, and I like to imagine I'm kind of cutting it off with scissors. And then I can look at the diene structure after I figured out what my dienophile is. So looking at this structure, these are the bonds that we're cutting off. Those are the bonds that were formed in the Deals-Alder reaction. So if we're going backwards, we're going to break those bonds. And so one thing to remember is just that in the overall reaction of Deals-Alder, we have this concerted mechanism that shifts the double bonds around. And so we have to remember that our dienophile is going to have a double bond in the precursor structure. So I'm just going to go ahead and kind of copy the overall structure over. So we've got this, we've got that pentacycle sort of structure. And then I have to remember that double bond. So we're just going to throw that double bond in that position. All right. And so now that we've cut out our dienophile, we can look and see our diene. So here we've got kind of the diene backbone. So I'm just going to draw that in the answer box. So we've got our backbone. And we need to remember that we're going backwards and we're reforming the diene. So just remember we've got to have at least 2 double bonds in there. And those double bonds are going to be connected to those new bonds that we formed. So we're going to have to shift the double bonds around, kind of like we did with the dienophile. And so in this case, they're going to go back to this position. And then we just need to put back our substituent CH3 there. All right, we don't have any more substituents or anything, so we should be good to go. And then one thing to keep in mind is that you can just check your work to kind of go in the forward direction and see what would happen if you reacted this compound with each other. And if it seems like it's going to be different, or if it is different than the structure that we're given at first, then you might need to reconsider the proposed structure that you have. But if you do it and it looks all good, then you should be good to go. All right. So going on to our last facts question, we have some multiplicity NMR questions. So for this first one, we're asked to find the number of carbon types. And so that's just going to be the number of different carbons in that structure. So I'm just going to start from left to right. So I've got the CH3, CH2 is obviously different, CH is obviously different. And then going down into the right, I have this CH2, CH3 group. And so one thing to consider when we're looking at NMR structures is we need to watch out for what I like to call twins. And so these twins are just compounds or groups that have the same connectivity and they're the same structure. And when we have these twins, what they do with the NMR is their signals will stack. So instead of seeing different peaks for these two CH2, CH3 groups, they'd actually stack and give us the same peak. So these are not actually different carbons when we're thinking about it in terms of NMR. So I'm just going to go ahead and number these the same as the first CH2, CH3 group. So we have 1 and 2 there. So then continuing on in the structure, we have a carbonyl that's different. We have a CH2 on the right side, and we have a CH2 off of that. And so while these two groups are both CH2s, we have to remember the connectivity and make sure that they're not the same structure. And so for this first one, going back to the left, we have a carbonyl, whereas this carbon CH2 on the right is not connected to a carbonyl. So those are going to be distinct. And then we're moving on to a double bond structure here. So this is going to be a separate carbon. And then this carbon over here is going to be our last carbon, our 8th carbon. All right, so for the number of carbon types, we've got 8. So now we're going to actually move on to the multiplicity of the hydrogens. So when we're looking at the hydrogen multiplicity, we need to make sure that we're looking at the neighbors of the carbon that's connected to that hydrogen that we're looking at. All right, so we're looking at multiplicity of HB. So we're going to be looking at this hydrogen right here. And so we're going to want to look at its neighbors. So going to the right, we have a carbonyl that does not have any hydrogens onto it. Going over here to the left, we have a CH2, and going down, we have a CH2. But we have to remember that we determined that these carbons are actually both considered the same in the NMR. They have the same structure and the same connectivity, so they're going to stack. So instead of getting something like 2 plus 1 times 2 plus 1, these are actually going to stack and give us 2 plus 2 plus 1. So this would give us 5 lines in our NMR peak. And again, that's just because they're the same carbon, they're considered the same carbon, and so the hydrogens would be considered the same as well. All right, so now we're going to look at HC. So this one's on an alkene, and so alkenes and epoxides are kind of unique in that even though these hydrogens might be connected to the same carbon, they will be considered distinct protons, and that is because of the geometrical factors. So when a alkene and an epoxide form, these bonds are actually kind of locked in place. And this is partially due to the pi cloud sharing. It kind of locks those groups in place. That double bond cannot rotate. And so the hydrogens are going to give distinct peaks because they're kind of adjacent to different groups. So for example, this H up at the top right here, that would have this CH2 group as its neighbor, whereas this hydrogen down here at the bottom right would have this other hydrogen as its neighbor. So since the neighbors are going to be different and that bond is locked in place, we have to consider the protons to be distinct. All right, so we're looking at this hydrogen C here. And so looking to the right, we have two hydrogens on this carbon, but again, we have to consider them as distinct protons because of that bond rotation factor. So these are each going to give us a 1 + 1 multiplicity. And then going over here to the left, we have two hydrogens. So that's going to give us 2 + 1. And so we're going to throw all that together. So 2 + 1 times, 1 + 1 times 1 + 1. That gives us 3 times 2 times 2, which is 12 lines on that NMR. All right. And so it would be the same thing for an epoxide. So if we had an epoxide like this, the hydrogens would be adjacent on the bottom, and then on the top, this hydrogen would be adjacent to, let's say, this R group. And so again, that's just because that bond can't rotate. Even though this oxygen is connected to the carbon through single bonds, that bond still wouldn't be able to rotate, because if it rotated, then the bonds between the oxygen and the carbon would actually have to break, and that would just destroy our epoxide, so that wouldn't happen. Okay, so we've got the multiplicity of our hydrogens, and now we're asked to look at the multiplicity of a carbon. And so when we're looking at carbon multiplicity, it's actually different from hydrogen multiplicity. And instead of looking at the neighbors, we're going to be looking at self. So we're going to be looking at the hydrogens that are directly attached to that carbon that we're asked to look at. So we're asked to look at carbon A. And so when we look at carbon A, we see that it's connected to this double bond carbon on the right. It's connected to a carbon on the left, and it's got a hydrogen down here at the bottom. So since it's only connected to this one hydrogen, this would be a 1 + 1 peak, and so that would give us 2 lines. Okay, so that is the NMR part of the facts. So now we're going to get started on our reactions. So you're going to see a lot of Orgo 1 reactions, so make sure that you're brushed up on those. There's a couple of new ones, but we'll get into that as we go on. All right, so for this first example, we're given O3, which is ozone. And this first step is actually going to be coupled with the second step. So it would be helpful to remember your coupled reactions. There's, I think, about 3 or 4 of them, 3 or 4 or 5. So make sure you're brushed up on those, because it would be very helpful to identify coupled reactions so you're not confused to heck why you don't know the second one. But what this first and second reactant does is it takes a double bond or a triple bond, and it cleaves and oxidizes those bonds. And ozone is specifically a milder oxidizing agent, and so it's going to give us ketones or aldehydes depending on what the connectivity of that carbon is. So we're going to look at our structure. It's going to cleave that double bond down the middle, and you can just put 1 and 2 together here. And so when we have a cyclic structure like this and it gets cleaved, what I like to do is I like to number it just to make sure I got the same amount of carbons, and I'm making sure that I'm putting the substituents in the right place. I'm just going to number that real quick. We've got a 5-carbon chain. We've got substituents at the 2nd and 4th carbons. And at 1 and 5 are going to be our oxidized carbons. So that's going to take that double bond and turn it into a carbonyl. And since these double bonds specifically are since this double bond is di-substituted and it's got 2 hydrogens there, these are going to turn into aldehydes. Okay, so now we go on to our third reaction. So we've got an acetylide group here, and we have an excess, and then we have then H3O+. So this carbanion is going to act as a nucleophile, and it's going to attack our partially positive carbonyls. And since we are given excess, we can go ahead and assume that this reactant is going to react with both of the carbonyls that we have in this compound. So this carbonyl is just going to go ahead and attack the carbonyl. That would kick up the double bond carbonyl to be on the oxygen, and that's going to go ahead and happen for both carbonyls. All right, so I'm just going to go ahead and draw out that triple bond. And then we've got the carbon that it's connected to with the O- now. And then we've got going to be our second carbon, fourth carbon. Those had our methyl substituents. And then we just have the same thing on the other side. All right. So this one had hydrogen. This one's also going to be O-. All right, and so the then H3O+ step is then going to take those oxygens and protonate them to be alcohols. So I'm just going to go ahead and put that there. And that's going to be the product of step 3. So our final step that we have here is going to be hydrogen and the Lindlar's catalyst, also known as a poison catalyst. And what this does is it takes alkynes and converts them to cis alkenes. And the reason why it makes them cis is that the reactant is actually like a physical metal, and our molecule here is actually physically attaching to the metal at that one side and adding the hydrogens. So we're just going to turn these triple bonds into cis hydrogens. So I'm just going to redraw our structure up here. All right, love our little tiny box. It doesn't fit anything. That's okay. Okay, so we've got our cis alkene. All right, and that's going to be the product of step 4. And that's going to be our final product. All right, moving on to reaction 2. All right, so we've got LiAlH4 and H3O+. Now, these ones are also kind of coupled together, but I'll show the product of step 1 first. And so what LiAlH4 does is it's a reducing agent, and it can reduce pretty much anything. You've got esters, you've got carboxylic acids, you've got ketones, and aldehydes. Now, the other reducing agent you might see is NABH4, and this one is milder, and it only does ketones and aldehydes, ketones and aldehydes. So just keep that in mind. We're given the stronger reducing agent though, so we're just going to go ahead and reduce this ester. So what happens is this LiAlH4 will reduce the carbonyl and the ester oxygen to be alcohols. So I'm just going to number my structure, make sure I keep my number of carbons straight. And so we're actually going to get 2 equivalents of the same 4-carbon alcohol. And you don't need to write the 2 equivalents or anything like that. Just writing 1 is fine. All right. And actually, I'm getting ahead of myself. So LaAlH4, we'll turn this into a alkoxide, and then step 2, the H3O plus, is where we're going to get that alkoxide to be protonated. So you can just write this as step 1/2. I just wanted to show a little bit more detail what happens with that second reactant. But moving on, we have a sodium metal reactant, and then in the next step we have an alkyl halide. So one thing to just keep in mind is that these two together are considered the Williamson ether synth, and it forms our ethers. And so if you see them right after each other, just keep that in mind. That might be what you're doing. But what this third reactant does, sodium metal, is it just deprotonates that alcohol. So we're just going to have that alkoxide again. All right. And so then step 4, what this does is it's kind of like an SN2 reaction. So this O- is going to attack our halide carbon. That bromine is going to get kicked out, and we're going to form our ether that way. And so when we look at this carbon chain that we're given, it's going to be a 4-carbon chain. And we have a 4-carbon chain, so this is going to form a symmetrical ether. So we've got our ether right there, just to make sure we've got the right number of carbons. All right, good to go. So that's going to be the product of those reactions. All right, so moving on to reaction number 3. I think this is actually meant to say CH3, but that's okay. So this is going to be our T-butoxide reagent. And so if you remember from Organic 1, T-butoxide is often used for E2 reactions. It's a strong base with the O-. But since it's bulky, it's actually going to give us the less substituted product. And the reason for that is just that the bulkiness of that base hinders that reaction. It's sterically hindered, and so it forms the less substituted product, or alkene, I should say. All right, so looking at the structure that we got here, so we've got our halide that would be performing in the E2. And so we've got a couple of hydrogens that we could potentially take off. So we've got this one on the left, and we've got this one on the right. And so, again, we just need to remember that this is our bulky base, and it's going to pull off a hydrogen that will give it a less substituted product. So if we pulled off the hydrogen on the left, and we formed that product, that bromine got kicked out, what would happen is we'd form this alkene over here to the left. If we go with the hydrogen on the right, same thing, that hydrogen would get taken off, that bond would go and form the double bond, and then we would be left with this alkene instead. And so the alkene on the left is trisub, whereas the alkene over here on the right is disub. And so we're going to go with this one on the right because of that steric hindrance. We want the less substituted product. Okay, reaction 2, we've got Br2 and CH2Cl. So this is going to add both of those bromines onto that double bond. And specifically, it's going to add them anticoplanar. So that's just when they're on opposite sides of that single bond. All right, so we've got our first bromine and we've got our second bromine. All right, so that's a product of step 2. Now we're going to go on to step 3. All right, we've got NaNH2, NH3, 150C, and then H3O+. So NaNH2 is our one of our alkyne forming reagents, and this one specifically is going to give us a terminal alkyne. The other one that you might get would be NaOH. That one would be an internal alkyne. Since we're given the terminal alkyne reagent, though, we're going to go ahead and make that alkyne on the end of our carbon chain. All right. And so you could draw it like that, or if you want, you can draw it in this kind of formation. I'll make it a little bit more clear that that's that triple bond on the end. All right, I don't know if that's better. Okay, so then our final reaction, step 4, we've got this HgSO4, H2SO4, and H2O. And so this is mercuric ion catalyzed hydration. And it's going to add an H and an OH to that triple bond. Now, the shortcut for this reaction is it's eventually going to form a ketone. But we will get to that in just a second. I kind of want to show the mechanism first to show how it does that. And so one thing to remember is mercuric ion hydration is a Markovnikov style addition. And so you remember that Markovnikov mercuric starts with M. So that OH is going to add to the more substituted side of that triple bond. So if we add our hydrogen and our oxygen on there, make that a little bit bigger. All right. So we're going to be left with a alkene. We've got a hydrogen added on, and we've got our OH added on as well. So what happens now from here is the double bond in the solution will actually protonate itself again, and it will form a carbocation at the alcohol carbon position. And so then what can happen is this alcohol, one of its lone pairs comes down to satisfy that carbocation, and we're left with a positively charged protonated ketone. So the last step of that mechanism is just that the hydrogen there would then be deprotonated by whatever base is in that solution. And so that's how we get our ketone from that reaction. And that's called enol keto tautomerization, or keto-enol tautomerization. So if you know that it's just going to form that ketone right off the bat, you're good to go. You don't need to show like all of this mechanism, but I just like to show it because I know sometimes it's not always evident why it just forms a ketone. All right, so that is the product that we have. Make sure I got all the right number of carbons. Okay, now we're good to go. All right, moving on to reaction number 4. All right, we've got an OH and we've got a Br, and our first reagent is going to be NaOH. Now what this NaOH is going to do, remember this is an ionic reaction, or ionic pair here. So this OH is going to deprotonate this hydrogen here. And the reason for that is because a OH hydrogen is going to be a lot more acidic than any CH hydrogen that's in here. So we're going to deprotonate that oxygen. Got that bromine there. And now we've got our O- on that carbon chain. So what happens with the second step, we've got acidic conditions. We've got this methanol in acidic conditions. And so what happens in this reaction, let me make sure I'm not getting ahead of myself here. I apologize. I am getting ahead of myself. Okay. So after this O- is formed, it's actually going to attack itself. and do intramolecular William ether synth. And since we've got this bromine here, that oxygen can attack that partially positive carbon that's attached to that bromine, and that bromine will get kicked out, similar to like an SN2 reaction. And so what that's going to form is that's going to form an epoxide. So it's intramolecular Williamson ether synthesis, but it forms our epoxide. Sorry, the bromine is not supposed to be there. Get out of here. Okay, so we've got our epoxide formed now. And so now what we can do is we can go on to the next reaction. So we've got our methanol and H+. And so we've got acidic conditions, and so this nucleophile is going to attack onto this epoxide. The first step is we're going to get that epoxide protonated and activated, and then that CH3OH will be able to attack the epoxide. And so just remember your BLAM acronym, and so that's going to say base attacks the least substituted side of the epoxide, and the acidic attacks the more substituted side of the epoxide. Or most, I guess. So since we have acidic conditions noted by that H+, this CH3OH is going to attach onto the more substituted side, which is going to be this side right here. So you don't need to show the mechanism or anything like that. Again, you just need to show the product of the reaction. And so what happens is that CH3OH attacks, that epoxide gets kicked up, and we form an alcohol, and that OCH3 adds on and is eventually deprotonated. But again, you don't need to show the whole mechanism. All right, I'm missing. Okay, there we go. All right, so we've got our last reaction here. This is a chromic acid reagent. So this is going to be a strong oxidizer. And so what this is going to do is it's going to take our alcohols and it's going to turn them to ketones or carboxylic acids, depending on if they're primary or secondary. So since we have a secondary alcohol, we're just going to form a ketone. So we're just going to draw our little structure and our ketone. And that's going to be the product of that reaction. The ether is not affected by the chromic acid reagent. It just stays as it is. It's safe. All right. Now we're going on to our NBS light 65C reaction. Okay, so this is going to be a reaction that we have to watch out for high temp or low temp. And so in this case, we're given 65C, which is going to be a high temperature. Usually I've seen high temperatures be around 50 to 65C, and then low temperature is pretty much always going to be 0C. So those are like the two options that you might see on your exam. And so NBS light, remember, is going to be our allylic bromination. And so that is going to be when the bromine adds on to the adjacent carbon next to the double bond, not on the double bond itself. And this is also a radical reaction. So just a few things to keep in mind from Orgo 1. So when we look at this, this molecule that we're given, we have two allylic sites. We have this one over here on the left, and we have this one over here on the right. However, when we look at the left half, this carbon here is actually already quaternary, and so we won't be able to add anything onto that because we can't add another group to make carbon have 5 bonds. Carbon can only have 4 bonds. All right, so then our only option that we're left with is this, the right side. And so the first step of the allylic bromination is it forms a radical at that allylic site. So I'm just going to go ahead and redraw the structure to be that allylic site. All right, so we're going to put our radical there. We've got our cyclohexene added on. All right, and so this is where we get into our resonance structures, and this is going to be very important for this reaction. You will have to show both of the resonance structures. And so what happens is a electron from the double bond will come in and react with the lone electron, the radical, and then the last electron in that double bond will get left behind. Very sad. All right. And so the resonance structure that forms is going to be, that's very poor. Let me redraw that. It's going to be this resonance structure that we have over here. All right, so now that we have our resonance structures, we have a couple of options to react with. So just starting from the left, if we react our bromine with the radical on this structure, we're going to get our bromine added on at this position. Our double bond would be there, and our cyclohexene would be there. If we look over on the right side at this resonance structure, we're going to form this product here with the bromine added on in that position. All right. So now that we have our two options, it's not on my paper for some reason, but we're going to have a major and minor product. And so this is going to depend on the temperature that you're given. So for high temp, the major product that forms is going to be the more stable alkene. And for low temp, if you were given 0 degrees Celsius, for example, the major product would be the more stable, the reaction with the more stable transition state. So now we need to look at these resonance structures and compare them to each other. So on the left, the radical that we have is going to be tertiary. And so radical stability is going to be similar to carbocation stability. So it's going to be tertiary, and then secondary, and then primary. So on the left, we got a tertiary radical, so that's a pretty stable radical. And then when we look at our alkene substitution, we have a di-substituted alkene. With the structure on the right, we have a secondary radical, and the alkene is going to be tri-substituted. So the left structure has the more stable radical, but the less stable alkene. The structure on the right has the less stable radical and the more stable alkene. And so then we're going to have to look at the temperature that we're given and go back to these rules over here. So since we're given 65C, that's going to be considered high temperature. And so we're going to go with the more stable alkene product. And so that's going to be this structure here, because it's tri-substituted versus di-substituted. So in the major box, we're going to take this product and put it in there. And then the minor product will just be the other product of the reaction. Okay, so that would be our minor product. So the high temperature major, so the high temperature major will be the low temperature minor, and vice versa. And the high temperature minor will be the low temperature major, and vice versa. So just remember high temperature versus low temperature. Make sure you remember which one corresponds to which for the stable alkene or the stable transition state. Okay, and moving on to our last reaction. All right, so this is going to be our Deals-Alder. We love Deals-Alder. So a few things to keep in mind. I like to make a checklist kind of what we need to look out for. So the first is just going to be the basic structure. And that's just going to be the structure of like the bonds after they react for a new product. The second thing is going to be stereochemistry. So our wedges and dashes and everything like that. And the third is going to be regiochemistry. And we'll get to that in a second. So I like to make sure that my bonds are kind of oriented towards each other. It just makes it a little bit easier on my brain to make sure I'm reacting everything properly. So I'm just going to redraw this dienophile. And then over here, looking at the diene, we have to rotate this bond around. And the reason for that is that this S-trans conformation, the double bonds are too far away to do the reaction properly. So we have to rotate that double bond to give them into that cis sort of conformation. And so when you have substituents, this can be a little bit difficult. What I like to do is I like to draw a line just down the middle kind of that single bond. And the bottom double bond is already kind of faced the right way towards that diene that we're going to be reacting with. So I'm going to switch that top bond around. So we're going to keep the bottom the same, and we're just going to rotate that top bond. So I like to draw this line down the middle, and then we just need to form basically the mirror product of this compound. So I know that this OCH3 is going to have to point down and to the right, and this CH3 is going to have to point up. And so then I can just redraw that, put it kind of closer to my dienophile. All right, get our subs in there. And now we can actually start doing our reaction. So like we looked at in the facts section, we have to make sure we're reacting this Deals-Alder correctly. So this double bond on the left is going to come in and attack the dienophile. And then the dienophile double bond is going to come in and attack diene. And that diene bond is going to get pushed back in towards itself, form a new double bond. All right. So let's go ahead and draw our structure. All right. And so what I like to do is I like to just double check and make sure I've kind of got that backbone right. So if I've got here in green my diene backbone, let's say in yellow we've got our dienophile backbone. All right. And then these are just going to be the two bonds that we formed in that reaction. Now we just got to add on our substituents. So on the bottom left, we've got a CH3 group. Oh yeah, don't forget. Got our double bond that was shifted into the middle. So that's where that double bond comes from. So we've got our substituents. That CH3 is going to be on that double bond in that position. On that top carbon, we've got a CH3 and an OCH3. And down on this dienophile, we've got that carbonyl. Okay, so that's going to be step one. We've just got the structure right. The next thing is going to be stereochemistry, and so that's going to be our wedges and dashes. So when we're looking at the diene stereochemistry in the product, the groups in the pocket are going to be on a wedge, and the groups on the outside of the pocket are going to be on a dash. And so what I mean by pocket is kind of like the inside of the structure, and the outside would be on the outside, kind of facing up and down, or pointing up and down. So when we look at the diene over here, this CH3 group is going to be on the outside, and so that's going to be put on a dash. And then the OCH3 was kind of in that pocket, so that one's going to be on a wedge. Now, when we're looking at this CH3, we actually don't, sorry, the CH3 on the bottom left, we don't need to look at stereochemistry for this one because in both structures, it's on an sp2 carbon. It's on a double bonded carbon. And so just remember that double bonded carbons are going to be flat. They're going to be planar. They don't have the wedge and dash stereochemistry like an sp3 carbon would. The reason why we have to consider it for this top carbon is because it went from sp2 and now it's sp3 in the product. All right. Another thing that we need to consider is what's called the endo rule. And so that is just stating that when these molecules react, they're actually kind of reacting like on top of each other. So this is a very poor 3D drawing, but the diene and the dienophile are kind of like on top of each other, and so that kind of pushes the stereochemistry of the dienophile in a certain way. And so when we're given a ring structure like this, the easiest thing to do is going to be to put the hydrogens, on wedges, because the endo rule will have the dienophile end up on dashes. And so with this ring structure, it's a little bit harder to show like dashes on the ring, and so it's perfectly fine if you just want to put the hydrogens on a wedge. All right, so we've got our stereochemistry, and so the last thing we need to worry about is regiochemistry. And so what this is what's called the 1-2-1-4 rule. And so this is just how the electrons get pushed around in the Deals-Alder reaction is specific to where the electron donating groups and withdrawing groups are in relation to each other on the ring. So what you want to do for this 1-2-1-4 rule, I'll put it over here, is you want to start from a electron donating group, and you're going to number around the ring to a electron withdrawing group. And so you're specifically going to start on the ring of the dienophile, on the ring of the Deals-Alder product. You're not going to start at a carbon itself. You're not going to start at a substituent carbon itself. So for example, when I look at this, we're going to start numbering, let's say from these donating groups, and then we're going to go around the ring towards the dienophile. So we've got 1, 2, 3. And like the donating groups, we're not going to the carbonyl carbon. The whole thing is considered the electron withdrawing group, including that carbon. So we're just going to where it's connected to on the ring. And so when we do this, we see that we have 1, 2, 3. So this would be a 1-3 product. If we start from the other electron donating group, this carbon on the bottom left, we also get 1, 2, 3, so 1-3 product. And so we don't want that. We want to get a 1-2 or a 1-4 product. And so the easiest way to switch this around is to just switch the side that donating group is on. So instead, we're going to put our carbonyl carbon up there. And so now when we look at denumbering, we go from 1, 2, and we get a 1, 2, 3, 4. So we'd get a 1, 2, and a 1-4 product. So that is going to be favorable. So we're going to put our electron withdrawing group in that position. And so another way you can think about this is just if you kind of flipped the dienophile when you're reacting it. So it'd be like reacting it. It's the same molecule, you're just kind of flipping it around. So I like to do that kind of as the last step because I just don't want to try and find the 1-2-1-4 product beforehand because it's a little bit confusing trying to keep all of that in mind when you're trying to do this structure. So I kind of like to do it step by step. But now that we've figured out the structure, the stereochemistry, and the regiochemistry, we can throw all of that into our box. All right, so we've got our wedges and our dashes. All right, don't forget your double bond. Don't forget your hydrogen wedges. All right. So it's a lot to think about, but if you do it step by step, it makes it a little bit easier. All right, and with that, we're done with reaction. So now we're going to move on to our mechanism. And so the first step I like to take when I'm doing mechanism is I like to identify nucleophiles and electrophiles. And so those are the groups that are just going to be doing kind of that electron pushing and stuff. And so that gives me a couple options. Sometimes you'll pick the wrong one to start if you're given multiple, but that's okay. If you have all your nucleophiles and electrophiles identified, you can just go back and look at a different one and kind of start from there and try again. So for this reaction, we've got a few nucleophiles. We've got a couple of double bonds, and we've got a couple of double bonds, and we've got an HCl. So we also have this oxygen down here. It's got some lone pairs. Those are also nucleophiles. So what I'm going to do is I'm going to take this oxygen, and I'm going to protonate it with that strong acid that we've got there. All right. Again, the most awesome part about these is redrawing everything 10 billion times. Love that. All right. All right, we've got a protonated epoxide. And so now what we can do is we can have a nucleophile attack this protonated activated epoxide. So when we do the first step, we form a Cl minus. And so that is also a new nucleophile that we introduced to the system. However, if we look at our product, we don't see any Cls in that structure. So we're going to try and look at something else. And so at this point, I might try and number the structures that I have. It's very useful, especially in mechanism, when you have to consider different carbons that could attach, like maybe methyl shifts and stuff like that. So I'm going to look at the structure that we have here and try and number it. And when I number it, I try to look for something that stays consistent. So as we can see, we lose an alkene. We have an OH that gets on there somehow. So I'm going to try and find something that's static that stays the same. So I'm just going to start numbering this one from left to right, sort of. So we're going to start here at the top and just kind of go around the ring. And I'm going to go around and try and get as many carbons as possible. So I'm going to go down, kind of around the ring, kind of up. All right. So it's a little bit wacky. We've got this kind of little snake structure going on, going around the ring. But it definitely helps to have that numbered. And so I'm going to try and mimic that as best as possible in the structure that I have down here. All right. 7, 8, 9, 10, 11, 12. All right, so we've got some substituents on there, but overall we have the same number of a linear chain. And it doesn't have to be perfect like nomenclature. It's kind of just what makes sense to you. So you could definitely number this a different way if you'd like. But overall, it looks like we're on the right track. So then, now that we have this protonated epoxide, we can have a nucleophile attack it. And so again, we have a Cl minus in there, but it doesn't look like we're going to need that in the final structure. So we're just going to go ahead and move past that. So when I look at the final product, I can see that there's this bond here between 6 and 11. And so when I look at the structure that I have, I see that 6 is actually part of one of those alkenes. And so an alkene is a nucleophile, and so I can use that to attack the epoxide. So I'm going to have this nucleophile come in and attack carbon 11, which is one of the epoxide carbons. And so that's going to kick that bond up onto the oxygen. So now we get to redraw our structure again. Lovely. All right. I apologize. Okay. Let me try writing it from the cyclostructure that we have. So we want to form that cyclohexane ring on the right. So I'm just going to start from there. Probably be a little bit easier to start with. And I'm just going to try and mimic it as best as I can. So we have 2 methyl groups on the bottom. We have that OH. We've got a methyl group up there. And so I'm going to kind of bring back my numbering system to kind of go back to a reference. So we've got 12, 11, 10, 9, 8, 7, 6. All right, and so 6 and 11 is the bond that we just formed, so that looks good. And so I'm just going to take the rest of what's attached to 6 and put that back on to the left. All right, so we've got 5, 4, 3, 2, 1. Got this bond here and got that there. All right. And so one thing to remember, when we do kind of a bond shift or like a cyclization kind of reaction, we have to make sure that we're keeping our carbocations in mind. So in the reaction above, we formed a bond between 6 and 11. And so we lost a double bond between 6 and 7. And so 7 is going to be the one that lost that bond. 6 lost it, but it formed a new one. 7 just straight up lost it. So we're going to have a carbocation on carbon 7 now because it lost that bond. So we're not quite done. So we need another nucleophile to react, and so we have another double bond that we could potentially use to react. So when we go back up here to our end product, we see that we actually do form a bond at carbon 7 with carbon 3. And so if we look at our structure, 3 is part of a double bond, so that checks out. So we're going to have that double bond go in and attack that carbocation. So at this point, I'm just going to straight up copy the final product. It's a little bit easier than trying to think super hard about where everything's going to form. So we've got a cycle, a bridged cyclic compound, and we've got a group coming off here, and we've got a group coming off here. All right, so I'm going to bring my numbering back, make sure I got everything all right. I think I'm actually missing that bond right here. All right, so let's bring our numbering back. We've got 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. So we're getting there. We're getting there. All right, we need to remember our carbocations again. So we formed a bond between 3 and 7 in this case, and we lost a double bond from 3 to 4. And so again, 3 lost a double bond, but it formed a new one, so that one's fine. And 4 lost that double bond, but did not gain a new one. So now we're going to have a carbocation at carbon 4. So again, we're not quite done, but we are almost there. So somehow we need to form a double bond between 3 and 4. And so we've got a carbocation here. And so what we can do is we can actually do a elimination reaction with a nucleophile in this system. So I'm going to bring back that chlorine that we were talking about. It's a Cl minus, got that strong basic character. And so if we need to form a bond between 3 and 4, then we need to somehow take off a hydrogen that will get us to that position. So I'm going to take off a hydrogen from 3 because that will then be able to push into towards carbon 4 and form that double bond. So that chlorine is going to take that hydrogen off. That bond is going to be left between 3 and 4 to satisfy 4's octet. And then we're going to get our final product. So you are welcome to redraw it if you would like. If you want to as well, you can also just show the arrow going up to the product, that would be good to go. And so just to make sure we have everything, we form our double bond between 3 and 4, and our substituents look all right. We've got the alcohol, the methyl groups, and the ethyl. So it looks like we're good to go on this mechanism. All right. So that's our mechanism done. So we're going to move on to synthesis. All right, synthesis is a little bit tricky. Always remember that you are working backwards. One thing that's helpful is to work backwards, but then kind of rework forwards, and just make sure that whatever you're putting down still makes sense. All right, so in this structure, we have a ketone here. We've got an ether. So we've got some interesting stuff going on. The last step, first step going backwards, I'm going to oxidize that, or it's hard to talk about if you're going backwards and forwards. So we want to form this ketone, so we're going to have to take an alcohol and oxidize it to that ketone. And so our oxidizing agents, with this one, since it's a ketone, we can use pretty much anything. So you have PCC, you have Jones, you have your chromic acid reagents, so Na2Cr2O7 and everything else that comes with it. Or you could do NaOCl, which is bleach. That's also an oxidizing agent. So any one of those would be fine in oxidizing this this structure. So going backwards, we'd have an alcohol, and again going forwards to oxidize that, we'd use one of these oxidizing agents to get to that ketone. So then we're just going to put our ether there. All right, so that's our first step. And so our next step, it looks a little bit tricky. Could potentially do a Grignard reagent, but that doesn't really quite look like it's going to work out. So one thing to keep in mind is that when you have an alcohol really close to another substituent, so we have this alcohol here and we have a substituent here, this ether, is we might have a epoxide reaction. So going backwards, we're going to think about having an epoxide, and we're going to see what sort of product we need to form that. And so here we can see that this ether added on. And so if we remember, we can have our alcohols attack epoxides to form that ether bond and then an alcohol. And so if we're doing an epoxide reaction, we need to watch out to make sure that we're attacking the right carbon. So don't forget, we've got our BLAM acronym. And so in this case, it looks like the substituent that we added on, this ether, attached to a more substituted carbon. And so when we have a more substituted carbon being attacked, that's going to be acidic conditions. So just make sure that we're putting that in there. And so if we want our ether to be an alcohol in the previous step, we're just going to go with cyclohexanol. And then we're going to have our acidic conditions. So just put H+, that's fine. All right. So then what this would do is our epoxide would be between those two carbons. All right. So at this point, I'm just going to work back this cyclohexanol. Also, I probably should have gone over this at the beginning. I apologize. Make sure you are reading your approved reagents. So we've got cyclohexene, alcohols of 3 carbons or less, and anything else that we might need. So sometimes you'll have cyclohexanol, sometimes you'll have cyclohexene. Always make sure to read your instructions carefully. But unfortunately, this cyclohexanol, we still have to work back a little bit. So working backwards, one of the main alcohol forming reactions that we know right now, is just going to be H3O plus with an alkene. And that's going to give us our OH. You could also use the mercuric catalyzed hydration. So HgSO4. And I believe it's H2SO4 and alcohol. Sorry, water, not alcohol. And then step 2 for that would be NaBH4. But the simplest one is just going to be H3O+. That one's perfectly fine. So that would give us our alcohol. So this is cyclohexene. That's one of our approved reagents. So we're just going to go ahead and box that off. Now we have to work with the other half. All right, so we're forming an epoxide. And what we can do with this one is we can use our MCPBA. And that's just going to take an alkene and turn it into that epoxide. That peroxy acid will take the alkene to the peroxide. So now that we've got this alkene, we've got to figure out a way to work these back to, again, cyclohexene and the 3 carbon or less alcohols. So to form this double bond, what we can do is we can do a dehydration. So if we have H2SO4 in heat, that will take an alcohol and turn it into a double bond. And so from there, we can do a Grignard reaction to get these two added on together. One little note, though, I'd like to mention for this one. So there are a couple options that we could do for this alcohol. We could either have this alcohol added directly to the ring, or we can have it put on to this linear chain. And so one thing to keep in mind is that when we're doing synthesis, we want to keep in mind the product formation if it's applicable. So in this case, we might have to consider the ratio of products that we would get. So when we do this dehydration, this is going to form the more substituted alkene. I'm going the wrong direction. Yeah. Direction. So when these alcohols react, this one on the right, for example, the one that we're using, we could either form a double bond at that carbon, or we could form a double bond at the carbon going towards the ring. And so this would give us a trisub and a disub alkene. Whereas this alcohol on the left, if we dehydrate it, the products that we could form would be something on the ring itself, or the same one that we have on the right, where we have it going off of the ring. And so, although there's only 2 options for both of them, we have to keep in mind the ratio of the products. So on the left, both of these this alcohol will form 2 different products, but both of them will be trisub products. And so that's going to give us a more equal ratio of product. And so we're actually going to form less of the product that we want. Whereas over here on the right, since trisub is more stable, we're going to form more of that product versus the other product, which is less stable. And so these are just arbitrary numbers. These aren't like official numbers or anything like that, but it's just to show that overall, this structure on the right is going to be more correct because we form more of the product that we want. And in real life synthesis, you really want to consider the ratio of the products because you want to form what you want to form. You don't want to form a bunch of other side products that aren't what you're looking for. All right, so anyways, from that tangent. So we've got our alcohol and we've got the one that we want to form the most of our product. And so we're just going to do a Grignard reaction to get these two going. So never forget your then H3O plus for Grignard. That's a free point. All right, and so we've got the left side, which is going to be our actual Grignard reagent, and then the right side is going to be our carbonyl. And so since this alcohol is going to be on the end, we're going to work it back, and it's going to be an aldehyde. So then, working back our Grignard reagent, we've got Mg ether, or I could do Et2O, and then that would leave us with our bromide. And then again, we need to go back to a cycloalkene. And so what we can do with this one is we can just do a simple HBr with that cycloalkene, and that will get that bromine added on there. All right, so we finished. We got this one back to cycloalkene. We just need to finish up this aldehyde over here. And so since it's an aldehyde, we want to turn it back into an alcohol, or we want to go from an alcohol to an aldehyde in the first, or the forward direction, sorry. And so the only way we can do that with our oxidizing reagents is going to be PCC. So we need to form an aldehyde. If we use anything else, it's going to be too strong and it'll take it to a carboxylic acid. So just keep that in mind as well. So now we're left with our 3-carbon alcohol, and we are done with the synthesis. All right, done with the synthesis, and our last question is going to be our spectroscopy. So the first thing for spec, you're going to want to calculate your unsat number. And so that's just going to be 2 times the number of carbon plus 2 minus the number of hydrogens. And I always recommend actually take the 1 minute it takes to do this math to make sure you're getting it right, because I still get this wrong sometimes when I try to do it too quickly, especially if you're taking the test and you might be a little bit stressed or you might be rushing a little bit. So with the numbers that we're given, we've got 2 times the number of carbons, which is 10, plus 2 minus the number of hydrogens, which is 12. All of that divided by 2. That gives us 20 plus 2 minus 12 over 2. And that's going to be 20 minus 10 over 2. And that's going to give us 10 over 2, which is equal to 5. All right, so a little bit tedious, and maybe it's just me, but for some reason, anytime I try to do that simple math, it just trips me up a little bit. So make sure you take your time and do that. All right, so we've got our unsat of 5, and whenever we have a unsat greater than or equal to 4, it's guaranteed to have a benzene, like 100% of the time. And if you still want more proof, go to the proton NMR, look between 6.5 and 7.5, and that is your benzene, hydrogen, proton peaks. So we've got an unsat of 5, so we've got unsat greater than or equal to 4, so it's like there's a benzene. When we go to check the proton NMR, we have some peaks in the 6.5 to 7.5 region, so that just confirms that we have a benzene. All right, so let's look at this IR quickly to make sure we can get our functional groups. First thing that we see, we've got this broad peak right here. Beautiful, we love that. That's an easy OH peak. We've got our carbon-hydrogen stretching. There's not really much we can get from there. And then we've got kind of very small, hard to see. But we do have a couple peaks over here at around 1600. And so 1600 is going to tell us if we have any carbonyls, if we have any C double bond N, although you won't really need to worry about that right now, or C double bond C. So pretty much all our double bonds. So again, we have a benzene, which has carbon-carbon double bonds, so that could be contributing to this peak. Another thing to check for when we have our double bonds, however, is to look between the 5 and kind of 6 region on the proton NMR. And so that's going to be our double bonding region. So while we do have some double bonds in the benzene and we have benzene peaks, we also have some peaks within this carbon-carbon double bond, regular alkene, not benzene, just regular alkene peak. So we might want to consider another carbon-carbon double bond somewhere in the structure. All right. So there's not really much else that we can get from the IR. The rest of this over here to the right is going to be our fingerprint region. There's not really a ton of stuff that you can get over here, although you might be able to see an ether peak. And you can use the table that you're given on the actual exam to kind of look at these regions, although I would just save any sort of ethers for last. If you think there's an ether, save it for last, because there's not really much other evidence from the IR that you can get to tell you if there's an ether. Okay, so now that we've gotten everything from the IR, we're going to go ahead and look at our NMR spectrum. And so whenever we have a benzene, it's very useful to first identify the substitution. So when we look at our benzene peaks over here, we have 3H. And so since we have 3 hydrogens, that indicates that there's 3 hydrogens on the benzene, and that's going to indicate that there's 3 regions where there's not hydrogen, so we're going to have substituents in that spot. And so there's a few different ways that we could have that. We could have them all spread equally apart. We can have them all on the same side, or we could have them in a little bit of a more awkward asymmetrical formation. And so these are our 3 options. If you try and move around the peaks, you'll just end up forming the same structure. So yeah, so these are our 3 options. And so when I look at this benzene region, these proton peaks, I see that it's very asymmetrical. So we've got kind of like a little doublet here and a singlet. And so that's going to hint towards this more awkward asymmetrical distribution. So we might have 1 hydrogen here, 1 hydrogen here, and 1 hydrogen here. And so this hydrogen over here does not have any neighbors. So it could be this peak right here. And then these 2 hydrogens are actually going to be splitting each other. So that could be that, that little doublet peak that we have there. And so again, these peaks are very asymmetrical. If we had something like this structure here, for example, you might see a more even peak distribution. Whereas here, they're all kind of split up, and all these substituents are going to be affecting them differently, so it's going to be more asymmetrical. So when I look at the substitution, I'm going to go with this asymmetrical benzene that we've got here. So I'm just going to put this down here so I can kind of look at my substituents later and add them on as I figure them out. All right, so we've got benzene, and that already takes out 6 of our 10 hydrogens. So we just have 4 more that we need to add on. So the next thing I'm going to look at is going to be this 5 to 6 region. And so this is going to be the carbon-carbon double bond region. And this is actually also going to be an alcohol region if we have an alcohol. And like we showed in the IR, we do have an alcohol. So we'll keep that in mind as well. But for now, let's look at these 2 peaks right here. So we have 2 hydrogens here that are pretty close together. And kind of like the benzene, where these peaks are very close, they're even closer over here. This is going to indicate that these hydrogens are very close together and potentially on the same double bond. And so the reason for that is if we have our carbon-carbon double bond, we have a terminal alkene here, and so these protons are going to be pretty similar because they've got the same connectivity, but they're not going to be exactly similar. Again, going back to that double bond not being able to rotate. So they will have steric effects from their neighbors that will slightly make them slightly different. But since their connectivity is the same, they're going to show up very, very close together on the proton NMR. So that's going to indicate that we've got a terminal alkene. And then the next carbon, the next hydrogen in the proton NMR is going to be this 1H peak singlet here. And so one thing to keep in mind is that alcohols do not split on the proton NMR. And that just has to do with the sensitivity of the instrument. It's not sensitive enough to detect any splitting for that OH. So when we have a small singlet peak 1H here, kind of in this region, that could indicate an alcohol because it's not splitting anything next to it, and it's pretty electronegative, so it's kind of deshielded. So we'll just put that off as our alcohol. And then this final structure in the C double bond C region slash C double bond, or sorry, OH region, I should say, we have this very small, lots of peaks. What is it? Signal, sorry, here. And it's this 1H. So we've got 1H on this carbon, and it's got a lot of neighbors. We've got what looks to be like maybe 6, 7 peaks there. But I'll say when you have a bunch of tiny little peaks like this, don't worry about getting the exact number of peaks, because oftentimes when you have a ton of neighbors like this, the peaks might not show up properly, or they kind of overlap, and it's not very pretty. So just don't worry too much about getting the total number of peaks for something that looks like this. Just keep in mind that this is going to have a lot of neighbors next to it. Okay, so going down kind of towards the less deshielded region, the more shielded region, we've got a 3H and a 2H. So this 3H, this is going to be a CH3. It's a singlet, so it doesn't have any hydrogen neighbors. And it's also very far down field to the left. Not as much as the peaks over here, but it's still very far downfield for just a alkyl group. So this could indicate that this is actually going to be attached to an oxygen. Oxygen is going to deshield that proton peak very strongly and put it down in this region. So we'll keep that in mind. And then for this 2H peak, this is going to be a CH2. It's a doublet, so that means we've got one neighbor going on here. And it's also kind of deshielded. It's not as much as the CH3, but it's still a little bit deshielded. So it's got one neighbor, the other side is not going to have anything. And that's going to be all of our proton NMR peaks. So with the carbon NMR, one of the biggest things that you can look at is the peaks, and you can count the number of peaks. And so this will tell you the number of different carbons in the structure, kind of like what we did with the facts section. And so what this does is it can tell us if there's any symmetry or any twins in the structure. So if we just go ahead and count all of our peaks here, we get 10 carbons. And so in our formula, we have 10 carbons. So that means everything is going to be a different carbon. And that can help, in this case, not very much, but if there's symmetry, it can help. Let's say we have 10 carbons and there's only 5 carbon peaks, then that would indicate that there's symmetry. In this case, that's not, we unfortunately can't do that, but that's still useful to know. We know that every carbon is going to be different. And another thing that you can do, you'll have the table during your exam. I unfortunately don't have the actual table, but I have just a general carbon-13 NMR peaks kind of regions going on here. So you can use this to compare and look at your carbon-13 NMR and kind of see what these peaks are going to be alluding to. So over here, kind of in the 0 to 80 region, we've got some regular alkyls from like the 100 to, let's say, like the 150 or like the 160. We've got some carbon-carbon double bonds, and so that kind of makes sense. Got some peaks here. We've got some double bonding going on, everything like that. But overall, we still got to put this structure together. So we know that we have a tri-substituted benzene. I apologize. We've got a terminal alkene, we've got a alcohol somewhere, and we've got an OCH3 somewhere. So we know that this CH2 over here is going to be connected to something with no neighbors. However, it's not as de-shielded as this CH3, so it won't be directly connected to an oxygen. And we can't put the alcohol on it, again, because it's not as far de-shielded, but also because that would just end the chain there. And we know that that can't be the case. All right. So, similar to the CH2 over there, we know that we can't put the alcohol on this terminal alkene because, again, that would end the chain. And we know that we need to put this whole structure together. All right. And so again, OCH3, it's not going to be a CH3OH because that's just going to be methanol, and we're not forming that. We have a whole 10 carbon structure. So we're not really left with many options for the alcohol. So I'm just going to go ahead and throw that on the ring as it is. And we'll see if that makes sense with the other groups that we have. All right. So what I'm noticing between the rest of these structures that we've got, we have a couple of CH3s that keep showing up. We have a CH3 here, or sorry, a CH here. We've got a CH here. So, especially in this very high multiplet signal, I'm going to think that maybe this CH is going to be between the terminal alkene and something else on the ring. And so I'm going to try and put this CH2 in that position as well. So we're looking at the CH, and we want to look at the splitting for this. So if we were to calculate the splitting for this, again, we have to keep in mind that the alkene hydrogens are going to be considered separate. And so this would give us a 1 + 1 times 1 + 1. And then the CH2 over here would give us a 2 + 1. So this would give us a 2 + 1 times a 1 + 1 times a 1 + 1. So 3 times 2 times 2 is 12. So that gives us a really high multiplet signal. And that kind of makes sense. We have this very small, lots of peaks signal down here. So I'm going to say that this is going to be our structure for this CH2 peak, this CH peak with all of its little peaks, and then this terminal alkene peak right here. And we also got rid of the OH peak. So that gets rid of a lot of our peaks. And so the only other option that we have, the only other puzzle piece that we have is this OCH3 here. And so again, we need to form a 10 carbon structure, so we can't just throw this CH3O onto the chain over here. That won't work. So the only other option really is to throw the OCH3 onto the ring, and then this structure that we just figured out onto the ring as well. And that's going to give us our final structure. All right. And so if you want, you can go back and kind of double check, make sure everything looks all right, make sure the splitting looks all right, make sure everything makes sense, especially considering like maybe de-shielding. But overall, it's kind of just a big puzzle that you have to put together. But it's okay. You can do it. And so overall, that's going to give us our structure. I'm just going to go ahead and put that in the box. And so for an example like this, where we have the tri-substituted benzene, You won't have to worry specifically about like which substituent goes where on the ring. So for example, it wouldn't really matter where you put the different substituents. We wouldn't be able to really gain that information from what we have here. You'd have to use more sensitive methods to kind of figure that out in real life. So overall, you're just going to have to figure out the substitution of the benzene, if there is one. And then you're going to have to figure out the substituents and their structures. So again, don't worry too much about where each substituent is on the ring, whether it's next to a certain group or not. The biggest thing is just getting that substitution and then getting the structure of the substituents right. But overall, that is going to be the spectroscopy, and that's going to be the end of that exam. All right. Thank you very much.